Andrew with HKN, and today we're going to plot the Fourier series and find the Fourier series for this function here, this sawtooth curve. So the reason we use Fourier series is because, well, there's no good mathematical expression for that. You can use Heaviside functions and stuff like that, but then you get an infinite summation anyway. And it's easier to work with exponentials and sine and cosine because those have easy derivatives and easy Laplace transforms and all those happy things. So we try to express them as sums of complex exponentials, and we know that complex exponentials are sines and cosines. So the way that we go about that is we're going to say we want to express this f of t as a sum from negative infinity to infinity of some set of coefficients that vary with k times e to the j 2 pi over t, which is your omega, nt. And that nt is also in the exponent, if that's not clear from that. So we're going to have to calculate what these coefficients are. So the first one we're going to do is C0. So C0 is your component at omega equals 0. You can also call that your DC component. So that has a little special formula because if you evaluate this and just plug in for n equals 0, you sometimes get stuff that can't work, like dividing by 0. Don't do that. So we'll first evaluate the DC component, or C0. So we're going to take C0 equal to 1 over, the period here is 4 pi. So we're doing 1 over 4 pi. The integral from 0 to 4 pi, because it's the integral over one period, f of t times e to the minus, but that e to the minus is going to be 0. Apologies. This one does not have anything on it. You're just integrating the function dt. So we have to figure out a way to express this function. So over one period, we can say that the function x of t is going to equal to, so it's just a line. It's a linearly increasing line. So the y-intercept is 0, so we just need the slope in order to get this. So the slope is a rise of 4 over run of 4 pi, so that should just be 1 over pi times t. So we're going to integrate 1 over pi t dt over this integral. So if we, interval. So if we take that, we get 1 over 4 pi squared, t squared over 2, evaluated from 0 to 4 pi. At 0, this is obviously 0. So if we just plug in 4 pi here, we get 8 pi squared, 16 pi squared, and then we'll have 8 pi squared on the bottom, so that should just give us 2. So C0 is 2. So that's a good start. Now we need, and there's obviously no phase at 0 because this wouldn't make sense if there was phase to your DC. So now we need this guy, which is going to be a complex number. It could be a complex number, it could be purely imaginary, could be purely real, or it could be a complex. So we're going to evaluate this for the rest of the k's as they go from negative infinity to infinity. So ck here equals 1 over the period again, which is 4 pi. The integral over the period from 0 to 4 pi. Sorry, my integral's a little off the screen there. This is a 4 pi. Of the function, which we said over one period is just 1 over pi t times e to the negative j, 2 pi over your period, but 2 pi over your period in this case is 2 pi over 4 pi, or 1/2. 1/2 n t dt. So doing that here, we can pull out the 1 over pi, so we get 1 over 4 pi squared. And then if we see here, we have the integral of t e to constants times t. In order to do that, that is an integration by parts, and we'll carry that out now. So if you're taking this integration by parts, you should say that u is going to be t, making du equal to dt. And if you're going to do this, you should also say that dv is equal to e to the minus j n over 2 t dt. Meaning that if you're trying to find v, you just have to take the integral of this. And the integral of e to the at is 1 over a e to the at. So you would get 1 over j n over 2. So it would be 2 over jn, that negated. But we can use the identity that 1 over negative j is just j. So what we end up with is j 2 over n e to the minus j n over 2 t, and no dt there because we just integrated that. So now we know our integration by parts formula. I'm going to move this over very quickly because I will run out of room very quickly. So we have same equality from up here, 1 over 4 pi squared from the 1 over pi there. The integral of uv, so this is j 2 over n t e to the minus j n over 2 t. And then we're going to have to subtract off the integral of v du. So that is j 2 over n, which is a constant with respect to t, e to the negative j n over 2 t dt, close brackets. So I'll box this off so that you don't get confused here. So this integral here is one that we've already taken. We already took the integral of e to the negative j n t. So this is actually the integral times j 2 over n. So j times j is just negative 1. So if we keep along with our equality here, we get 1 over 4 pi squared j 2 over n t e to the minus j n over 2 t plus 4 over n squared e to the minus j n over 2 t. Close brackets. And now we're going to evaluate this at our limits for t, 0 to 4 pi. So if we put in 4 pi here, we end up with, I'll distribute this as I plug in. So I get 4 pi is going to cancel with one of the 4 pi's down here, so we get 1 over pi. So this becomes j 2 over pi n e to the minus j n 4 pi over 2. Or you can simplify that more to 2 pi. And what you'll find here, I'll find later, is that this is going to be 1. So this is e to the j theta. If you know your cosine and sine, you can prove to yourself that for any integer value of n, which this only takes integer values of n, I used n instead of k. I apologize for the notation switch. For any integer values of n or k, I guess I'll say here, n equals k. For any integer values of n or k, this is going to be 1, so it can go away. Now we continue on with our plugging in of 4 pi, but we're going over here now. And we have this same exponential here, so this is always going to be 1. So we just get plus 4 over n squared. Now we're going to plug in 0. So we have to subtract the 0 plugged in. And what you get is this first term here will always be 0 because 0 times anything is 0. And then over here we have an e to the 0. I forgot to do the 1 over 4 pi here. So so this actually isn't 4 over n squared. It's 4 over n squared times 1 over 4 pi squared. So that should be 1 over pi squared n squared. Not that it'll matter in a minute, but you'll see. So if you plug in a 0 here, it's also 1. And e to the 0 is always 1. So we get the 4 over n squared times 1 over pi squared, 1 over 4 pi squared. So we end up with 1 over pi squared n squared. Close this. And we get that these terms cancel. And obviously minus 0 doesn't matter. So what we end up with finally is that ck, and I'll make this a k now, is j 2 pi k. So that looks good, but in order to make this easier for plotting magnitude and phase, which we will do in a second video, we're going to change this form here. So we like to have, this is our rectangular form. It's a purely imaginary number, but it is in rectangular form. In order to make our lives easier to plot magnitude and phase, we would like to have it in polar form. So in order to convert this to polar form, this is just a real number, so that's our magnitude. So our magnitude is 2 over pi k. But j here, j is an angle of 90 degrees because that is what it corresponds to the y-axis in the imaginary real plane. You can just say that j is e to the j pi, or 90 degrees. So e to the j theta, where theta is 90 degrees. So we just get e to the j pi. And so this is ck. So you could actually write the exponential Fourier series now and say that f of t, the original function over here, f of t, is equal to the sum from k equals negative infinity to infinity of ck e to the j n t over 2, where ck is equal to 2 over pi k e to the j pi for k not equal to 0, and equal to 2 for k equal to 0. So that is your Fourier series in exponential form representation of this function over here. So in the next video, we're going to plot the magnitude and the phase response of this guy, and we'll see what it looks like as we vary our frequencies, and which frequencies, higher or lower, are contained in this function. If you want to try to guess beforehand, I would suggest looking at the phase and magnitude of your coefficients. That might give you an idea. Until next time, see you later, guys.